Welcome to this next in the series of how-to videos. This one is on transformers. So if you are a trilogy candidate, there's not too much for you here. But if you're doing physics GCSE, then this is absolutely for you. So we have a question which says the diagram shows a transformer with a 50 Hertz AC supply connected to 10 turns of insulated wire wrapped around one side of the iron core. So here's our core, here's our 10 turns, here's our 50 Hertz AC supply. And there is a voltmeter with 5 turns. So we've got 10 turns here and we've got 5 turns here. So we are already expecting this to be a step-down transformer if we know our stuff, because we have fewer turns in our secondary than we have in our primary. So here's our primary. That's the one that the supply is connected to. And here's our secondary, where we take our transformed potential difference across. So what type of transformer is shown in the diagram? Well, we've already said it's step down. We know it's step down because there are fewer turns in the secondary than in the primary. To be fair, though, when we get to the table below, the data will show us that it's a step-down transformer. This is an old question, and switch mode transformers are not on the syllabus anymore at this time in 2022. So you don't need to worry about that. They're far more interesting than these. Far more difficult to explain how they work, but this is what you have for your laptop, your Chromebook, your iPhone charger. That's what these are, switch mode transformers. They don't look like this inside, but that's a whole different story. So step down transformer because there are fewer turns in the secondary than in the primary. Table shows values for the potential difference of the supply and the voltmeter reading. 6.4, 3.2. So we have a step down factor here where this is half of that. Well, that's what you'd expect because you have half the number of turns here. If you remember your formula, the ratio of the potential differences across the primary and the secondary is equal to the ratio of the turns in the coils, primary to secondary. And we also have, just for information, it is the ratio of the current in the secondary to the primary. So fill in the values. Well, this has to be half of that. So that'll be 1.6. And this has to be twice that. That'll be 12.8. Transformers are used as part of the national grid. Part 2, how are the values of PD in the table different to the values produced by the national grid? Well, the national grid values are much larger. You might have 400,000 volts for the long distance cross-country transmission of electricity, whereas you're looking at 3, 6, 12, 13 volts here. So the national grid values are much larger. That's all we're looking for here for 1 mark. Transformers will work with alternating current, alternating supply, but will not, note bold, not work with direct current. To describe the difference, AC changes direction periodically. DC only one direction. That answers that. Just to remind you, if that's our potential difference in volts, that's our time in seconds, that is DC because it is not changing direction. that is AC because it is changing direction. So it has to go one side and then the other of the 0 volts line. So you have positive voltages here and negative voltages here for it to be AC. Just changing size like this doesn't make it AC. It has to change direction. And finally, for 4 marks, explain how a transformer works. Well, there's so much to say here. So we have the alternating PD across the primary produces changing current through the primary, which produces a changing magnetic field around the primary. I'm just going to say P there to save me writing on the next line. The secondary sits in this changing field. So a PD is induced. We have to use the word induced across the secondary due to the changing magnetic field through it. You can also talk about the soft iron laminated core. Soft means easily magnetized and demagnetized, which means you lose less energy doing that, magnetizing and demagnetizing and remagnetizing the other way. Iron, because it is magnetic. Laminated, because when you put your conductor in this changing magnetic field, this being a conductor, that changing magnetic field induces a PD across it, like you have here. And what you get then is eddy currents. Literally, little swirling currents in your conductor. Now, by laminating it, literally by making it out of sheets and having those sheets separated from each other by lacquer, varnish, so they're not, there's no electrical connection between this sheet and this one, then you have the same amount of iron, so you get the same amount of magnetism around this iron when it becomes magnetized by the field around it. But because the sheets are separated by your insulator, then the electrical resistance of this lump of iron is now much, much bigger, which means that the eddy currents are much, much smaller. What these do is cause heating. And the heating, of course, is a waste of energy. So you lose energy from your system if you have those eddy currents. By laminating your soft iron core, you reduce the eddy currents by increasing the resistance. So what you do is you have, basically you have your changing magnetic field due to your primary. So there's the magnetic field around the primary. You have the magnetic field, which is due to the core. It gets magnetized and demagnetized. So these should be coinciding, these zeros, but I'm struggling to draw. So you have the magnetic field due to the core, and the field through the secondary. What color? How about green? The field through the secondary then is the addition of these two. So the field through the secondary changes at the same frequency, but you have a bigger change. And the induced PD across your secondary depends on the rate of change of the field through the secondary. There's more to it. Come back at A level and you'll explore more. But it depends on the rate of change, how quickly it is changing. So it's changing from here to here in this time, whereas this field, just due to the primary, is only changing from here to here. So you have a smaller change in the same time, so you have a smaller rate of change of field. This is a bigger rate of change of field, which gives you a bigger induced PD. So that's why you have your soft iron core. So going back to my answer, the alternating PD across the primary, well, you're told that already, aren't you? You're told you have this alternating PD across the primary. Here we have AC. So that's probably not worth a mark, but having it in there allows me to write the next bit. You have this changing current through the primary. That produces a changing magnetic field around the primary. The secondary sits in that changing magnetic field, so you have a potential difference induced across the secondary. So this is a key word. You see the logical progression. This is what you're given in the question, so you can't really claim credit for that. You're not going to get any marks for it. But this alternating PD across the primary produces a changing or alternating current through the primary. That's worth a credit because you weren't told that. That current through that coil of wire produces a magnetic field because that's how you make an electromagnet, right? You pass current through a coil of wire. The coil behaves like a bar magnet then. So because the current is changing, the field is changing. So you have this changing magnetic field around the primary. The secondary coil sits in that field. Now, that might not be obvious from the diagram, if I can find the diagram, there it is. But in a real transformer, this coil would be wrapped over the top of that one. It's separated like this, so it's easier for you to see what's going on. But actually, this coil would actually be wrapped over the top of that one. So that all of the field from the primary goes through the secondary. So the secondary coil does actually sit in that magnetic field, absolutely in the field, surrounded by it, filled by it. So going back here then, that changing magnetic field around the primary, the secondary is sitting in that field, which means there is a PD induced across the secondary due to that changing magnetic field. So there's our 4 marks. You could also talk about if you have a complete circuit, go back to our diagram here. If we had a lamp in there, or a motor or something, that would give us the complete circuit. The induced PD across here would then drive a current around that complete circuit, so you get an induced current. So again, come back at A level and you'll learn more about that. So what have we done? We have identified what kind of transformer it is by looking at the number of turns relative to each other in the primary and the secondary. If there are more turns in the secondary than in the primary, it is a step up. If there are fewer turns, it's a step down. Here we have 10 in the primary, 5 in the secondary, it's a step down. We have done some simple arithmetic here. We've given the example, 6.43.2. To be fair, they didn't have to do that. They could have just said it's a step down transformer and get you to work this out. But here you have the numbers which would have led you to the answer to the previous question anyway. This is half of this, so therefore this has to be half of that. And going the other way, this has to be twice that. This question is just asking you, do you know the sorts of values the potential differences are in the national grid. This is asking you the difference between AC and DC. Very often asked that question. And then this is the big money part. How do transformers work? There's lots of stuff to say here, but those are the 4 key points, I think. A different question might require you to get into the soft iron core. What's it about? Why is it laminated? Maybe even what do we mean by soft? Although I've never actually seen that question, but I thought it was worth mentioning that soft means easily magnetized and demagnetized. It does not mean that the iron is somehow squidgy. It isn't. So there it is. I hope you found that helpful.